You're live, Seth.
Okay. All right, everybody. That was a long intro, but it gave you the chance to stock up on something to eat or perhaps to drink. This is another episode of SETI Live. I'm Seth, Shostak, an astronomer here at the SETI Institute. And today, it's really kind of a special SETI Live because we're going to talk about that instrument you can see behind me from the Wayback Machine, the Arecibo Radio Telescope. We'll be talking with Michael Busch, who is an astronomer at the Institute. And his work is more than just motivated by intellectual curiosity. It might have a real influence on your life. In fact, it could conceivably save your life. Now, before we get started, I just want to remind you of something that many of you know, but not everyone, and that is that the SETI Institute runs on your donations. Yes, when it comes to much of the research, some of the kind of sexy research at the SETI Institute, in particular, SETI, for example, there's no government funding for that, so it's dependent on you guys. So if you're enjoying these SETI Lives or the SETI Talks that we also have, other events like movie night and so forth at the SETI Institute, we hope you'll keep that in mind. Okay, so with all that said, let me introduce Michael Busch. Michael Busch is an astronomer at the SETI Institute, and he has used the Arecibo telescope behind me in a mode that most people don't even know about. It has a transmitter. Very few radio telescopes have a transmitter. It's all about listening. That this one has a transmitter. Michael, well, welcome to SETI Live, and tell us exactly why you need that transmitter on this giant antenna, or what was this giant antenna.
Okay. So, as Seth mentioned, the Arecibo Observatory had a set of high-power radio transmitters mounted up on the platform above the main dish. So, Arecibo is still mostly a 300-meter, 1,000-foot wide dish embedded in a sinkhole in the middle of Puerto Rico. We have mounted up at the top, had mounted up at the top of the platform. In that platform is a transmitter. We send out a coded radar beam. It goes out into space. We have some asteroid flying by the Earth, and it bounces off. The beam bounces off the asteroid. It comes back to the Earth. This technique, we also use the Goldstone Solar System radar, which is in Southern California, and it's been done a few other places. It lets you time very precisely how far away the asteroid is. You measure the time of flight of the radar signal going out and coming back, and you measure the speed of the object by the Doppler shift of the radar beam going out and coming back. And like you might track airplanes near an airport, you can track positions of the asteroids and where they're going very precisely. This lets us forecast asteroids' orbits out much further in the future than we otherwise can and predict potential future Earth impacts. And ideally, rule them out.
Okay, well, Michael, there was a lot to unpack there. You're bouncing radar from the transmitter on this dish. I'm going to talk about it in the present sense. We'll get back to what happened to the telescope later, but you bounce radar off it, the radar comes back, the dish is big enough to get that weak signal, that bounces off these rocks in space. You can tell how fast they're moving away. I mean, what are you trying to learn? Are you trying to learn the shape of these things? You're trying to learn their orbit more precisely so you can say whether they're going to hit Earth? What's the major driver?
So there's several aspects here. Back in the 1980s, scientists realized that a dinosaur killing an asteroid landed in what is currently the Yucatan Peninsula in southern Mexico 66 million years ago. This motivated a lot more research to track all near-Earth asteroids that you can and chart all their orbits. Arecibo and other radars' assistance with that is primarily astrometry, measuring very precisely where they are and how fast they're moving. There's a second level to it, where we want to know, if we have an asteroid out in space, what is its shape? This is an asteroid called 2008 EV5. It has this spheroidal shape. For those who are watching this with the audio, I'm holding up a 3D print of the shape model of an asteroid that we observe with Arecibo. It has this equatorial bulge, ridge around the equator, similar to the asteroids Bennu and Ryu that have been visited by spacecraft recently. And we know the shape is very common among near-Earth asteroids because Arecibo has observed so many of them. We do that delayed Doppler imaging I mentioned, measures also both where it is, but if we increase the resolution, we can resolve the object. The time of flight of the radar signal out, some part of the surface is a little bit closer to the Earth by a certain number of nanoseconds, or equivalent to distance from the Earth. And we just step back along the distance from Earth in one direction. As the object spins, parts of it are moving towards us relative to the center, and parts are moving away. And that Doppler shift gives us a second dimension of resolution. This is a very peculiar way of imaging things. It's not normal pictures like you'd see just looking at the thing if you were standing next to it or a spacecraft was next to it. But if you get enough data from enough different angles, you can figure out what's going on.
Okay.
Arecibo has observed hundreds of asteroids this way.
Let me just say, give us some idea, because that thing you're holding up is not exactly to scale.
So the real asteroid 2008 EV5 that I have the 10-centimeter wide print of in my hand here is about 400 meters across. That's a quarter of a mile. Arecibo observed it when it was passing a few million kilometers away from the Earth. So it's 8.5 times further away than the moon for this one.
Yeah.
And so you observed for a certain number of seconds for the radar signal to go out and come back. Then you switched back to transmit. And transmit again, and then that signal comes back down. You switch to receive, and we go back and forth this way.
Okay. Give us an idea, I mean, just to put this in a sort of a popular context. If that asteroid, which I have to say does look a little bit like this asteroid Bennu, which,
there's some interesting science behind the shape here, which we can talk about if we have time.
Okay.
I don't think we will.
But for many people, they may wonder, well, I don't really care what it looks like. I may care about how big it is, and I certainly care about what its orbit is, because I want to know if I'm going to meet it face to face. If something like that actually hit, Central Park in New York, what would be the consequence?
So an asteroid 400 meters wide, like this one, makes a hole in the ground several kilometers wide if it hits the Earth. And there are a few such holes in different parts of the world. Something like this hits somewhere on the Earth every few 100,000 years, mostly over the ocean. But there are a few that have landed on the land that we can see the craters. Meteor crater in Arizona, for those who are familiar with it, that was a 50-meter wide object, so a lot smaller than this, and it still made a pretty big hole. We'd like to know about these things in advance so that we can tell people to get out of the way. Or if we've got enough notice and the thing is big enough, we could talk about moving the asteroid off course. And NASA has a project with ESA called DART that's designed to demonstrate asteroid deflection on an asteroid called Didymos, in part because Didymos has been observed extensively with Arecibo, and thus we have lots of data on that object.
Okay, so this sounds like important work. In particular, you don't want a big hole in central Manhattan. I mean, that deprives people of opportunities for shopping and dining.
Manhattan is a small area, though. More relevant is Siberia.
Okay, but Siberia has been hit more than once, right?
Yes, because it's such a large space. It has had 2 significant impacts in the past 100 and some years.
Yeah, okay. All right. So Arecibo has collapsed. Let's just briefly, I think most people know that story, but in case you don't, maybe we ought to go over quickly what actually happened. Maybe you could show your diagram there. I explain.
I hold up a whiteboard basically thing here. I have a printout showing the structure of the Arecibo Observatory as it was designed. We have the 300-meter wide circular dish. Again, if anybody's working with this out video, I'm just showing a picture of a circle, basically. In the middle, there's the platform, which is suspended up about, is it 500 feet, Seth, between the platform and the dish? 400
and some, yes.
So you could stack however many football fields that is go vertically, and then 3 across. So this is a very big thing. And then on the hills around at sort of 4 o'clock, 8 o'clock, and 12 o'clock, if this was the face of a clock, there were 3 tall towers. And those set a series of cables from each of the towers to the platform. So it's supported at 3 corners, triangular platform over the dish. And then underneath the platform, you hang a arm that can turn around 360 degrees in each direction and move back and forth along that arm. There's a set of receivers, so the telescope can look at anything that's passed within about 20 degrees of vertical.
That's an important point, because
you can't tilt this thing sideways. It's too big for that.
Right, exactly. Mechanically, you can't make the kind of dish you see all the time in the movies, which, tilt and follow things across the sky. So you move, as it were, the receiver around, and it turns out that if you're willing to observe at whatever time of day the object you're interested in kind of passes overhead, you can observe about a third of the universe, a third of the sky with this instrument, or could have. Now, you were talking about the application to detecting or mapping, really, asteroids, their shapes, their orbits, and so forth. Now that Arecibo is gone, how does that affect our ability to find these potentially dangerous objects?
So Arecibo was the most sensitive radar facility in the world. It was one of the two most sensitive radio telescopes. The other is the FAST telescope in China, but FAST can't have a transmitter. It's not designed to do that. It doesn't have the big platform. It can't hold that much weight. So Arecibo was the most sensitive radar we had available. It's about 20 times more sensitive than the Goldstone solar system radar that I mentioned. The radar signal strength goes off very steeply as objects get further away from the Earth. It's the fourth power of distance. 1 over r squared out, 1 over r squared back. So it really helps to have a really big dish to do this. In terms of radar astrometry, Arecibo could detect about not quite twice as many asteroids as Goldstone can. Goldstone can do about 60% as many.
Well, wait a minute.
Also, tricky because the Goldstone solar system radar is mounted at the Deep Space Network antennas, which NASA primarily uses to talk to spacecraft. So Arecibo was primarily doing astronomy and radar work, radio and radar. Goldstone is primarily talking to spacecraft. So scheduling can be an issue. If Mars is up, we don't do much asteroid work at Goldstone.
Yeah. I follow you there. Just again, you give people an idea of what the situation is. People weren't terribly interested in sort of mapping all the asteroids, or at least the big ones, the kind that could take out a lot of life. Up until, well, you mentioned the fact that we had recognized that the dinosaurs, and I think it was like 60 or 70% of all other species, were taken out 66 million years ago by a rock. But they also saw comet Shoemaker-Levy plunge into Jupiter and make holes.
That also was motivation.
Yeah.
So in the 1980s, people started realizing asteroid impact hazard. Then CCD cameras became widely available for doing optical astronomy, and that helped find a lot more asteroids because they're more sensitive than old photographic film, which Seth had to deal with, and I never did. They
still deals with
the upgrades to the Arecibo radar in the 1990s. I think probably were driven more by that sort of my recognition than the Shoemaker-Levy stuff. Just when Shoemaker-Levy happened, though, in the 1990s, that again motivated a lot more work here. Similarly, the Chelyabinsk impact over Chelyabinsk in Russia almost 8 years ago now also increased recognition of smaller asteroids are still a hazard too. We're not going to have any extinction level asteroid event in the next several hundred years. We've checked all those objects. None of them are going to hit anytime soon. But we still like to know about any regional sort of event. So there's still a big motivation to track as many asteroids as we can. And now we have lost one of our best tools for doing that.
Yeah, okay. So asteroids bigger than a half a kilometer do a lot of damage if they hit. But there are a lot of asteroids that are in that size range, such as the one that you showed as a model there. Do you have any idea what percentage of the dangerous asteroids? I mean, obviously, if something's the size of a house, which is kind of what the Chelyabinsk rock was, I mean, okay, they can kill a few people, but they don't wipe out an entire city. But if you have something, a kilometer or so across, I mean, that's very dangerous. Do you have any idea what percentage of the asteroids of that size still remain to be, mapped?
So Arecibo detected maybe 10% of them with radar, but there was a bias there because we give priority to observing the asteroids that are potentially hazardous. The near-Earth asteroids that can't currently come very near the Earth, Arecibo could not detect. And also, we wouldn't have bothered trying to detect them usually because they're not really an impact hazard. There is one asteroid called 1950 DA, which we observed with Arecibo over quite a long time, starting in 2000. It has a potential Earth impact in the year 2880. It is a kilometer wide. If it hit, that would be a serious problem. But it's also 860 years from now. So we hopefully have time to resolve the uncertainty there.
And also
absent Arecibo, which I had hoped would let me rule that out a couple of years from now.
Yeah. Let's say very briefly again what happened to Arecibo. You sort of described the architecture of this telescope, and tell us what happened. I mean, things began to go south, although it's already pretty far south, began to go south in August. Before you do that, I'm just going to mention that we have people around the world that are paying attention. In Norway, Nederland, Berlin, Ciudad Juarez down in Mexico, Finland, Warsaw, Poland, Assam, India, and Karnataka, India. And again, just to remind you, if you find these things interesting, but frankly, even if you don't, but if you find these things interesting, consider the fact that we would appreciate any donations that you would like to give to the SETI Institute. And if you're wondering how to do that, you actually could go to the Institute, but the doors are all locked. I recommend that you just go to the SETI.org, which is the website, and you'll find all sorts of instruction there about how to donate. Okay, go ahead, Michael. We're talking with Michael Busch here. He's an astronomer at the SETI Institute. And tell us what happened to this world-class instrument.
So, as I mentioned before, we have the main Arecibo dish in the sinkhole in limestone karst. So you've got these big limestone blocks, hundreds of meters wide, hills around the observatory. On top of those hills are 3 towers that are holding up the platform. So for those who are at the video, we have here, again, the schematic. Over here is Tower 4. So again, there's 12, 4, and 8, like they were the arms of a clock. Tower 4 here, back in August of this year, one of the auxiliary cables supporting the platform linked to that tower slipped out of the socket at the top of the tower and fell down onto the dish. That did significant amount of damage to the dish just directly from the impact, because it's basically a whip coming down. And it wrapped around and smashed into some of the stuff up on the platform. At that point, all observing stopped, and focus became repair the telescope. The schedule there was that they would have people come down in the first part of November to start repairs and get replacement cables to be installed in the middle of December. And they ordered 2 replacement cables because they've been wanting to repair the cables on the telescope for a couple of years because they were noticeably getting damaged. The situation became a lot more fraught in November because just before the repairs were slated to start, one of the main cables on the Tower 4 snapped. This one broke in the middle. And now everything on the platform is very unstable. So the observatory was designed that auxiliary cable can break, a main cable can break. It will still be structurally sound. You can go up and fix things. It was not designed to handle 2 cables breaking before the first one was fixed. At that point, the National Science Foundation ordered a bunch of separate expert engineering reviews from a bunch of independent engineering companies. And they also called in a consult with the Army Corps of Engineers. At the end of November, they decided that the repair options at that point were no longer safe for anybody to attempt. The plan at that point involved things like using a helicopter as a sky crane to have people rappel down to the platform and slice off bits of it to reduce the load on the structure to the point that it would be safe to work with. So they then decided they would do a controlled demolition of the structure, collapse the towers into the dish. Before that could happen, a bit over a week ago now, another main cable on Tower 4 snapped. And then the entire structure collapsed. And that is what we are at.
Yeah, okay, so the damage is no longer what you would call superficial. You know, those cables are about the thickness of my arm. I mean, they're these are not
3 1/4 inch cable on the main ones. Yeah.
Yes, something like that. And, of course, they're made of various steel, smaller steel wire. Just like the cables on the Brooklyn Bridge or the Golden Gate Bridge or any other suspension bridge. They don't break. The Brooklyn Bridge was completed in the 1880s, and they haven't had to replace any cables. Any idea why the cables were breaking at Arecibo?
So there had been some degradation for many years. The main cables there are 57 years old, as old as the observatory. The auxiliary cables were installed in the 1990s. There had been discussions a few years ago that cables are starting to degrade. We're noticing a few of the outer fibers on the cable bundles starting to snap. We should probably get new ones. There was not funding available to do that rapidly. The degradation inside the cables was apparently more than expected based on the outside appearance. It's hard to do remote sounding on the inside of a cable from 100 meters up in the air. Since observing has been shut down, they have been flying a quad-rotor drone around the observatory to look at the cables since the August break, and they could see additional strands starting to go poing, poing. You could hear them sometimes, apparently. If I understood Angela Vasquez of the observatory operations team correctly. So once the auxiliary cable broke, everything else was right at the limits of the stress it could support. And then once the second cable broke, things were past the limits they could handle.
But I'm still wondering, Michael. I mean, again, all right, lack of maintenance. They should have replaced some of these cables when they began to see failure. But on the other hand, why are they failing at all? I mean, is it just too much load on these cables? Is it because of the
they were not running past the load design? They were running maybe 70% of 60-70% of design strength when the cable snapped. What caused that? Good question. They would like to recover the cables and figure that out.
Okay. I just want
to just to give some context here again for people. When the telescope came down, there was a few people from the observatory staff on site. Nobody was right near the telescope. Everything within a tower height of the towers was excluded. The observatory control room, which is on the north side behind Seth, because he's got it in his backdrop in Zoom here. The observatory control room was on the north side there, was not hit by anything particularly big during the collapse. Angela Vasquez, the observatory operations team, was in there at the time, as they had been assigned to briefly go in, collect a bunch of computers, and take them downhill out of the way. So I'm really glad they're all safe. There were a couple of remote cameras. Carlos Perez had set up a camera outside the control room between there and the North Tower. And that is the video of the Arecibo collapse that you can find from the National Science Foundation. There's also the drone footage. Adrian Vague had been flying that drone around every day in the morning doing the survey. And he happened to be doing a survey at just the time that the last cable went and everything collapsed.
Yeah. Oh, okay.
Now, the main platform, of course, is still, the cables on the southeast side of Tower 4 snapped. It's still held briefly by the cables on the other two towers, so the platform fell down towards the northwest. And it took parts of Tower 4 with it when it came, and then parts of the other two towers eventually snapped off because they weren't designed to handle that load all by themselves. And then everything sort of dragged across and smashed into the northwest side of the dish.
All right. I've seen emails from a number of people about this failure, and some of them attribute it to, deferred maintenance, and certainly that's an issue. We've already talked a little bit about that. Others point out that, of course, Arecibo has been hit by storms, and it's true. It's in the path of a lot of the hurricanes that come up through the Caribbean. I remember more than once having to abandon our observations and get to the San Juan airport quickly to get a plane out of Puerto Rico. But, this thing was very conservatively designed. And as you say, I hope they can figure out what went wrong. Now, we're getting toward the bottom of the hour, and we want to get to some of these questions. There are a number of questions coming in. I might also mention that Sweden, Argentina, Manitoba, Canada, which is very close to Churchill, which is the cultural center of Canada, have also joined the discussion. So it looks like you want to say something further here, Michael, and then we'll go to questions.
So, regards to the damage from the hurricanes Irma and Maria 3 years ago now, there was significant damage to the observatory at the time. Not all of that was ever fully repaired. There was a timeline to do that, and before that happened, there has been a collapse. There was also some possible damage from a series of earthquakes that hit Puerto Rico more recently, and again, never fully addressed.
Yeah. Okay, let's go to a couple of questions where, we've been operating in receive mode, or you have, and we're going to go a little bit into transmit mode where you can ask some questions. You know how to do that, I presume. And if you don't, then your questions will be overtaken by people who do. The first and most obvious question is, well, what happens in terms of the work being done at Arecibo. And we've been talking about radar observations of asteroids, but Arecibo was the prime instrument for studying pulsars. I used it years ago for studying galaxies, small galaxies. The first planet around another star was actually with two of them. It was found with Arecibo, believe it or not. And, and then, of course, the radar work. All of these are, and SETI, by the way, I didn't mention SETI. We were down there for years trying to find ET with this instrument because it's very big, very sensitive. What happens now, Michael? I'm an astronomer and I'm doing pulsar work or whatever. Do I just quit and take a job at the local gas station? What happens?
So no one facility can do everything that Arecibo did. In terms of radio astronomy, I mentioned the FAST telescope in China, in Jishu. They've finished construction now. FAST is a 500-meter dish, but they only use 300 meters of it at a time. So it's about as sensitive as Arecibo was. But it can look over a much larger section of the sky because it has a much smaller receive platform pod held up by the towers, and it can go way off to the side. And they have active surface to some degree, so they can move the dish around rather than needing a big platform up top. That can do a bunch of the radio astronomy stuff that Arecibo did. It can't do all of it. It doesn't have the receivers at the present time. There will be some efforts there, presumably, but I have limited information.
All right. Do they have plans to put a transmitter on it? Is there a transmitter on it?
It's not possible to put a transmitter on FAST. It's not designed to do that. There's been some discussions of what we call biostatic radar observations. You transmit from another telescope and you receive with FAST. I don't know the state of that plan. Yeah. We do this already with the Green Bank telescope in West Virginia and the radar telescopes that we have available in California. For the radar stuff, there is a proposal to put a radar transmitter on the Green Bank telescope. This gets a little complicated logistically because the Green Bank telescope is in the National Radio Quiet Zone. There are not supposed to be any really high-power radio transmitters in the radio quiet zone because the telescope is there and usually doesn't want any other sources of radio happening. It's probably okay if it's a transmitter that the telescope is in control of, but it hasn't happened yet. And that's a matter of maybe 5-ish years to actually build such a thing. Somebody asked in the questions here, is there any possibility of reconstructing Arecibo? That is a very good question, and that is being talked about quite a lot amongst astronomers right now. So the collapse took out about 30% of the dish. Some parts of it are still there, relatively intact. And there are some antennas that are still intact. The main platform, of course, is now collapsed down on the side. The towers have been snapped off at the tops. The degree to which the bedrock is still structurally sound is not clear to me because 1,000 tons of platform coming down, smashing into the rocks is going to do something. If it's safe to rebuild on the site, and that will be a question for the structural engineers to assess, then one could envision rebuilding Arecibo using potentially some of the existing dish has survived and building new towers, a new platform, new system. And people are talking about what would that look like. But it also would be a very large project and take many years to do.
I had an email from Francisco Cordova, who is the director of the Arecibo Observatory, about just this point. What would it cost to repair Arecibo? And the number he said obtained here was $120 million. Now, there are some people who could fund that out of their pocket, but that's still a lot of money. And the National Science Foundation is not inclined to do that at the moment. But so suppose they say, okay, that's it with Arecibo. It's been a good run since the early 1960s. We're going to shut it down. We're going to put money for astronomy into other instruments. What happens to Arecibo? Do they just sort of abandon the site and it becomes, ground zero kind of memorial? What happens?
There will need to be quite a lot of cleanup, regardless of if there is a rebuild or if there is not a rebuild, because you have now a very large quantity of steel and concrete and a sort of interesting materials like lead counterweights and beryllium detector elements all smashed up and piled together in the sinkhole. Now the sinkhole, the limestone is porous at the bottom. The water drains out. You don't want to be leaching lead from the counterweights into the water table. That will be bad. So there's going to need to be a lot of cleanup of the Arecibo site before any rebuild, and also before eventual closure, if that is what happens.
They say it would take $40 million just to truck away the parts.
I don't know the estimates there. Depends a bit on what you want to do in terms of cleanup.
Yeah.
You want to remove everything, as versus you say you were going to try to salvage some of the dish, then the amount of stuff you have to haul is less. And the rebuild cost, the number there varies widely too, depending on exactly what you would want to build. If you want a different radar transmitter, higher frequency, different power requirements, if you need to rebuild the towers, if you can salvage parts of the towers, if you can salvage some of the dish, or if you completely rebuild the dish, the numbers there's a wide range.
Here's another question. Will this motivate us to put space-based asteroid monitoring satellites on orbits inside Earth's orbit and pointing out from the sun to search for near-Earth objects? Can we do this from space?
So we can do asteroid discovery from space. There is a spacecraft called WISE, the Wide Field Infrared Space Explorer, which has done this for many years. It was originally designed for astrophysics, and Amy Mainzer, who was at JPL and is now at the University of Arizona, realized she could use this to find lots of asteroids from space that were hard to find from the ground. She is now leading a project called NEOSM, Near Earth Asteroid Surveillance Mission. And this is a NASA project. You put a satellite just inside Earth orbit at the Earth-Sun Lagrange point. And from there, it can image large chunks of the sky that we have trouble seeing from the ground. Sorry about that noise. And then you can find asteroids quickly. But it doesn't replace the need for radar follow-up, because the precision you get from optical infrared measurements is much less than from radar astrometry. So the time out into the future, which we can predict potential impacts and rule them out, becomes much less. And you cannot put a large radio telescope in space. The largest radio telescope anyone has ever put in space is 10 meters wide. Arecibo is 300 meters wide. The Goldstone telescope is 70. The Green Bank telescope is 100 meters. Each of these individual telescopes is many times bigger and far, far more massive than the International Space Station. The technology to do big radio telescopes in space simply doesn't exist.
But we could put it on the moon, build it.
That is outside of any planning horizon that I can forecast here.
Well, I'm disappointed to hear that, Michael, that you're not going to put a telescope on the moon. But it has been suggested. And in fact, you could take a lesson from Arecibo, right? There are craters on the moon, and you might want to put it on the far side of the moon as seen from Earth, because there you don't get the interference from Earth.
If we were talking about building things a kilometer across on the moon, this would be a very different discussion.
It would, but it's something that people do talk about. And in fact, some members of the International Astronautics Congress have even decided which crater on the backside of the moon would make the best site for a new telescope. Okay, well, we're going to wrap this up soon. Any other questions you have, please get them to us. I'll say just very briefly something about SETI at Arecibo, because SETI was done using the Arecibo telescope for decades, actually. And some of that was work done by the SETI Institute, Project Phoenix. In the late 1990s, we had the equipment, the receiving equipment, the specialized receivers that are used to look for signals from ET, if you will. We had them all put into a container, a shipping container. You see them on the backs of trucks and trains all the time, these big containers. We had one of those outfitted with the receivers, put into a big cargo plane, taken to San Juan, and then trucked up to the observatory, where it was parked next to the observing building there. And we would use this twice a year for a couple of weeks. That was the amount of time that we got to observe at Arecibo. Obviously, it was a very competitive telescope. And the big advantage to having something at Arecibo was the big advantage of the telescope, the fact that it's big and it could find weaker signals. And that ended, as I say, about the turn of the millennium, and we went to other places and eventually built the Allen Telescope Array. But there was another very clever idea that was conceived of by people at the University of California, Berkeley, and elsewhere, where they would use a second receiver on the dish to just pick up data all the time, no matter where the antenna was, directing its prime attention. You could always have a second camera there, sort of like a second camera on your car, which doesn't tell you what you're about to back into or anything you're going to hit in front of you, but stuff's off to the side. But that's okay. You don't know where ET is. And that was also used to provide a lot of the data for the SETI at Home project, which is the University of California, Berkeley grant. Okay, here's another question. Maybe this will be the last question, Michael. Can other facilities such as the GMRT, and I think that's an Indian radio telescope, but be repurposed? You can tell us about that. Be repurposed as a space radar. Would that be a cheaper alternative to, for example, rebuilding Arecibo?
So I mentioned the Green Bank Telescope in West Virginia. There is a plan right now to put a small demonstration transmitter on the telescope, and that could eventually build it to a larger one that could reach Arecibo's sensitivity. But that works at much higher frequencies, 30 gigahertz or so, because it has to. In order to reach Arecibo's sensitivity, you need a much higher frequency to get as narrow a beam on a smaller antenna. That makes it susceptible to weather variations because the atmosphere is pretty consistently transparent between about 1 and 10 gigahertz. And then above that, it gets, every time there's a rainstorm or a snowstorm, you get much worse performance, which optical astronomers deal with all the time. We're kind of spoiled in the radio because we don't care about the weather that much. But if you go to the high frequencies, you do. At the same time, things like the GMRT, which was mentioned here, the Giant Meter Wave Radio Telescope, those are much longer wavelengths. At that point, you're not actually doing radar astronomy anymore. You're studying the Earth's atmosphere. And Arecibo had a very active program to do that. They had radio transmitters that worked down in tens of megahertz range, very long wavelengths. And they're studying the Earth's ionosphere, upper atmosphere. And there's interesting science there. And that can be done with other facilities. Arecibo, again, was very sensitive for this, which is why it was so popular. But that will be done elsewhere, not at Green Bank and the higher frequency radars we use for radar astronomy, but there's facilities in Norway, elsewhere in the United States, there's stuff in Canada, various parts of the world for studying your ionosphere and atmosphere with radar. And those will keep working.
Okay, one last question. It's actually from somebody in Berlin, and they're asking, okay, what about you, Michael? I mean, this was an instrument that you used for a lot of your research. How does this affect you personally?
We are now replanning everything we had proposed to NASA to do for the next 3 years. We still will be doing as much radar observations as we can with the Goldstone radar facility. There's some stuff with the working between NASA and groups in Australia with the Canberra Deep Space Network, and they've been doing some good stuff. The sensitivity is not as great again. There's discussions of proposing to NASA, the National Science Foundation, other funding agencies for the money to rebuild Arecibo or build an equivalent. And we also have a very large quantity of data that we've taken with Arecibo over the past several years that we have not finished working on. So I probably should analyze all that and write it up. That'd be a good thing to do.
Okay, so at least in the near term, you have a legacy of data to take
all the data from Arecibo is archived. They copied it all down, offsite backups, and everything in the control room is still there. So all the data archive is safe.
Yeah.
And okay. We'll be working with that for many years to come, both for radio astronomy and radar.
All right. It sounds like no immediate concerns for you there. My immediate concern is to thank all the people that tuned in today for this session of SETI Live. Remind you that the Institute is a nonprofit, and any contribution you can offer by going to the SETI Institute website, SETI.org, we would appreciate, because that, of course, facilitates much of our research. And I urge you to check out check out the website, but also you should be signed up to get information about these kinds of events, SETI Lives, and also SETI Talks, and other things like SETI Movie Night. All of that you can get in your mailbox, and I'm sure you're really lacking for email these days, and we will send that to you. Just go again to the website and sign up. I want to thank you all again. I want to thank Michael Busch. A very interesting, very timely topic, and we'll see you next time here at SETI Live.
One last thing, Seth, if I may.
Well, you may.
The Arecibo Observatory's education and public outreach programs are still running. If people wish to support them, there are options to do so on the Arecibo website, which is naic.edu.
There you go. There you go. So it's an extraordinarily interesting little museum of astronomy that they have right there on the site. Okay, we'll see you next time.